Hello, and welcome back. So in the last video, we were just talking about and kind of interpreting the output from a paired t-test. And recall that a paired t-test uses the same people or the same plots of land or the same whatever, same things pre and post some intervention. Okay, so there's a time component to this whole thing. Okay, at two points. Okay, and based on this t-test, we were able to answer the question: is there a difference between reaction times between boozing it up? Okay, so before you booze it up and after you booze it up. Essentially, the practical question there is, does alcohol affect reaction time in pilots? And we are able to say, oh yeah, it does. Okay, because our p-value was below 0.05, we're able to trust that the difference that we saw here was not due to random chance. It is due to some mechanic kind of back in the background. In this case, it's booze, and then a bunch of physiology behind that. Okay, of course, that's not our job to determine the physiology. It's the scientist's job. We're just here to say that there is a difference, and for the whole population of pilots, that difference in reaction time is contained in this interval. Very cool, very cool. So what I want to show you now is how we can kind of cheese a paired t-test by doing something a little simpler, okay? And I'll kind of show you the mechanics behind what a paired t-test is actually doing. So I'll say it now. What a paired t-test actually does, sort of, I'm being very general here. Essentially, it just says, okay, take the difference between each person and put it in a new column, okay? So in our case, we had two columns of pre and post. What the computer does in the background kind of is that it makes a new column of the difference between the pre and post, or the post and pre, okay? And then it tests this thing. It tests what it's saying here, so that difference is not equal to 0, okay? So it's some known value of 0 in this case, because the difference of 0 means that there is no difference, okay? So I'm going to show you how to get that same result, the same result from a t-test, but by just using one single column of data. Whoa. Okay, so let's just go ahead and get into it. So I've got a little one sample t-test here. Now, essentially what I want to do is I want to take this and subtract this and put it in a new column over here. Okay, now we have a bunch of different ways we can go about doing this. I am partial to the tidyverse way of doing it. Okay, and if you go back to the PowerPoint, you'll kind of see some foreshadowing. We're going to be using this function called mutate. Okay, so I'll get that out of there. Of course, since we're using a tidyverse function like that, we need to incorporate some English into it, some kind of a nice natural workflow into it. Okay, so what I want to do is I just want to add something to our data. Okay, when we use the mutate column, it just adds to it. So we need to specify the thing that we want to add to. Okay, which in this case is going to be in these data here. We're going to add a new column. Okay, let me get rid of this too. Okay, so what do I want to do? Well, I want to tell the computer that I'm going to be using the data from the original data. Okay, so essentially I'm just going to be overriding what's already in here. Okay, by just adding a new column from the stuff that's based in this data set. Okay, and then I want to, well, I actually only want to do one thing, is I want to mutate, kind of a weird function name here, but you know, we have Hadley Wickham to thank for that. What I want to do is I want to mutate a new column. I want to make a new column based on these two other columns. Okay, so what do I want to, what do I want to call it? Let's see. Let me just go back here. I've got pre-capitalized, post-capitalized. So let's just call it diff, D-I-F, capital D-I-F for difference. Okay, and what is that going to equal? Okay, well, if we recall from the paired t-test, the kind of order here matters as far as the way that we subtract things. So let's see, I think I said, yeah, the post has larger values, at least for most of them, than the pre. So let's just go ahead and say post minus pre. All right, and is there anything else I need to do? The answer is no. The answer is no. So I can name this anything I want. This left-hand side here, anything I want. Very similar to how I can name anything over here that I want to. kind of going back up to naming and creating data, or at least reading in data, okay? So whatever, it's just going to be a function of post minus pre. So if I run this, no errors, no warnings, that's great. Look at that. So now I have a difference column here. I now have a difference column, all right? And so we can see that the difference in reaction times for this first pilot of ID1 is 76 milliseconds. So post was 76 milliseconds slower than our pre. And we can kind of go down from here. We see the two lunatics here that somehow got better after drinking, right? But that's, that's okay. What we're about to do, that paired t-test accounted for that. And the test I'm about to show you is also going to account for that. And we also saw this person with a reaction time of no change. And that's that pink line over here. Ah, very cool. If I wanted to, I can make a histogram of that. And I use the $ to grab just that one column. Not histogram, sorry. I'm getting the base R and the tidyverse stuff mixed up. And we see the kind of distribution here. It's wonky. It is whatever it is. Since we have paired data and at least, a decent amount of paired data, this is fine. We're not going to so much worry about the overall shape here. Okay. Very, very cool. Very, very cool. Now, I want to test if this difference column is any different than a known value of 0. Okay. A known value of 0. And how am I going to do that? Well, we did do that with the paired t-test, right? What the paired t-test did essentially is just create a column in the background kind of invisibly and then compare it to 0. See if the mean of these differences, the mean of this column is any different than a known value of 0, okay? Okay, so if I just wanted to do a one sample t-test, because I just want to use this one column here, right? One sample. Essentially, we know we're cheesing it, right? But the computer doesn't know that. The computer does not know that this is a function of these two other things when we throw it into the t-test function. It's just going to think that it's a single sample by itself, okay? And I want to compare it to some known value, okay? So if I go in here and say, okay, take reaction, and I just want to test DIF, okay, this single line of code is going to run a one sample t-test. Whoa. It's wild. Okay, and if I run that, check it out. It's telling me I'm doing a one sample t-test with the data that I supplied, and it gives me the stuff that we're kind of used to seeing, or at least starting to get used to seeing. Okay. Do we notice any difference here? Do we notice a single thing that is different? Well, let me go back to the old PowerPoint here and show you. So here's a little comparison. So we have our paired t-test up top that's comparing the two columns and the difference between those two columns, the paired difference between those two columns. And then we have our one sample t-test down here that's comparing our difference, our paired difference that we created ourselves, okay? A t-value, 2.68. T-value, 2.68. Degrees of freedom are the same. The p-value is the same. The 95% confidence interval is the same. Oh my gosh, the only thing that's kind of different is the mean of the differences and the mean of x, right? So the paired t-test gives you a slightly more sort of tailored to paired differences output as far as what it says it is. But aside from that, oh my gosh, that's it. That's it. The values are the same. The estimates are the same. The test statistic is the same. Oh my gosh. So check it out. We were able to cheese, the same stuff that a paired t-test did, but with just a single column, okay? So in this case, we are able to make the same conclusions. Is there a difference between the pre and the post, okay? Or is this difference column that we created right here, any different than 0, right? So essentially what this is doing is that well, we have, if we go back, way back to those two histograms, right? Essentially what this is doing is it's plotting a histogram of these things, the theoretical sort of distribution that these things come from. And then another similarly sized distribution centered at 0. Okay, and it's just checking the overlap there. That's not actually what's happening in the background, but visually you can kind of think of it in that sense. Okay, so the paired t-test is saying take these two and compare the paired differences, and our one sample t-test is saying take this single sample and compare it to 0. Okay, oh my gosh. And you get the same thing. I think that's great, right? So is that column any different than 0? The answer is yes, it is, because our p-value is below 0.05, right? It's below alpha. And we even have the hypothesis, the alternative hypothesis listed here. True mean is not equal to 0. The true mean of our paired difference column is not 0. And we know that that paired difference is going to be contained in this interval for the whole population. Oh my gosh. So same conclusions, we're just doing it in a slightly different way. I think that is awesome. I think that's great. And we can kind of see, let me move here. Let me get rid of that. It's not a very good figure. Move that there. Booyah. Okay. So the paired t-test accounts for the fact that we have the same people over some period of time. And it's accounting for the fact that they're going to be all slightly different from each other, which is awesome. I think that the paired t-test is super, super strong because it can account for the difference in people, right? The difference from person to person. And in fact, can account for these kind of weird behaviors as well, where we kind of go against the trend of everyone, and not even with any kind of trend, right? We're looking more at a person-to-person sort of comparison here. Paired t-test gives you the same information that a one sample t-test does. We have to make our own data for a one sample t-test, but it is pretty simple to do so. With the paired data or the paired t-test, we just chuck in the columns and specify that it is truly paired, and that's that. So with that, oh my gosh, you return to the FAA to collect your 100K, and we say, since the p-value is less than 0.05, we reject the null hypothesis and say that there is a difference between pre and post booze, we'll say. Practically, we're saying that booze does affect reaction time. Okay. The difference in means, we can come back here to either of these, right? To either of these, because we have the same information, right? And it's given to us. The difference in means is 195.6 milliseconds. 195.6 milliseconds, and is t, right, standard units away from 0. So our difference that we saw here theoretically is 2.68 standard error units away from being no different at all, right? No, there is no difference at all. And that's what the t value is specifying, that we're this far away from this claim, okay? Or this far away from there not being any difference, okay? So 2.6832, we'll just say 2.68, whatever standard error units away from 0. We can be 95% confident that the true difference in means, that the true difference between not drinking and drinking booze is between, which one do we want? Well, it doesn't matter because it's the same information, right? So 30.69 milliseconds and 360.5. So we'll just say, well, I've already forgotten the first one. We'll just say, just kind of rounding here, 31 milliseconds. And what was the other one? 360? Yeah, we'll say 361, just to round up, milliseconds, okay? Oh my gosh. So for the whole population of pilots, okay, that there's a 95% chance that the true population difference in means, the true population effect essentially of booze on reaction time is contained in this interval here. Oh my gosh, I think that's awesome that we can do that. We're able to make a claim for every single pilot that is at least similar to the sample that we have. we're able to make that claim for every single pilot that they're going to be affected on average by this much. Okay, booze is going to slow down the reaction time by this much. I think that's awesome. I think that's super cool. Now you might be wondering, well, 31 to 361 is kind of a big range. Should we? How can we, get a better idea of the actual? Because this might be, this is kind of big. This is kind of big, but at least the range is. If we were to sample and get more people in our study, so instead of 10, maybe 100, it turns out that this interval here would become narrower. The reason is because we're starting to grab more from the population, okay? And the bigger and bigger our sample is, the closer we get to the population, in this case, pilots, okay? So the more pilots we sample, the more pilots we're able to recruit, then the closer we are to getting to the truth there as far as the population goes, okay? So the bigger the sample, the more like it becomes to the population, and the narrower this becomes, okay? So the bigger the picture, the better, right? And the fact that we have paired data make this claim very strong, okay? In the next video, I'm going to show you what happens when you do the wrong test, okay? And then after that, we'll kind of go over the little recap here, and that'll be it for t-tests, okay? So we've had this for about, we're getting into about 2 weeks of this material, depending on how fast you watch these videos. But this, these kind of things here, these claims are true across all t-tests, right? As far as the overall structure, okay? Oh, boy. Okay. With that, I'll see you in the next one.